Chapter 17, Temperature and Heat. Temperature and heat covers the zeroth law of thermodynamics, thermal expansion, heat capacity, the first law of thermodynamics, heat transfer mechanisms. You can find them in a timeline. The zero law of thermodynamics. Temperature. Mechanics deals with the mechanical energy of system and is governed by Newton's laws. Thermodynamics deals with an internal energy of the system, thermal energy, and is governed by a new set of laws. The central concept of the thermodynamics is temperature. Temperature is one of the 7 international system-based quantities. Physicists measure temperature on the Kelvin scale, which is marked in units called kelvins. Although the temperature of a body apparently has no upper limit, it does have a lower limit. This limiting low temperature is taken as the zero of the Kelvin temperature scale. Room temperature is 290 Kelvin. This is the Kelvin. When the universe began around 137 billion years ago, its temperature was about 10 to the 39 Kelvin. As the universe expanded, it cooled, and it has now reached an average temperature of about 3K. We on Earth are a little warmer than that because we had lived near a star. Without our sun, we too would be 3K, or rather, we would not exist. The lowest temperature reached in lab up to now is T equal to 0.38 times 10 to the minus 12 K at University of Bremen, Germany, which is published on the 30th August 2021, Physics Review Letters. Temperature is one of the 7 international system-based quantities. Physicists measure temperature on the Kelvin scale, which is marked in units called kelvins. Although the temperature of a body apparently has no upper limit, it does have a lower limit. This limiting low temperature is taken as the zero of the Kelvin temperature scale. Room temperature is 290 Kelvin. The zero law of the thermodynamics. The property of many bodies changes as we alter their temperature. In thermal equilibrium, all physical properties of matter, of system, are stable. That means they does not change with time. The zeroth law of thermodynamics. If bodies A and B are each in thermal equilibrium with the third body T, then they are in thermal equilibrium with each other. Now, body A is in equilibrium with thermal T. Body B is in equilibrium, thermal equilibrium with system T. Then, if we touch A and B, nothing will change. They are in thermal equilibrium. In less formal language, the message of the zeroth law is everybody has a property called temperature. When two bodies are in thermal equilibrium, their temperatures are equal, and vice versa. The zeroth law, which has been called a logical afterthought, came to light only in the 1930s, long after the first and the second law of thermodynamics has been discovered and numbered. Because the concept of temperature is fundamental to those two laws. The law that established temperature as a valid concept should have the lowest number. Here, the 0. Measuring temperature. The triple point of water To set up a temperature scale, we pick some reproducible thermal phenomena and quite arbitrarily assign a certain Kelvin temperature to its thermal environment. That is, we select a standard fixed point and give it a standard fixed point temperature. Liquid water, solid ice, and water vapor, gaseous water, can coexist in thermal equilibrium at only one set of values of pressure and temperature. The temperature is 233.16 Kelvin. The pressure is 0.61 kilopascal. This is the bulbs. This is the ice, water vapor. Figure shows a triple point cell in which the so-called triple point of water can be achieved in the laboratory. By international agreement, the triple point of water has been assigned a value of 273.16 Kelvin as the standard fixed point temperature for the calibration of thermometers. The pressure is 0.61 kilopascal. That is, T3 equals 273.16 Kelvin, called a triple point temperature, in which the subscript 3 reminds us of the triple point. This agreement also set the size of Kelvin as 1 over 273.16 of the difference between the absolute zero and the triple point temperature of water. The degree of Kelvin is equal to the degree of Celsius. Note that we do not use a degree mark in reporting Kelvin temperature. This one. Okay. It is 300 Kelvin, not 300 degree of Kelvin. And it is 300 Kelvin, not 300 degree Kelvin. The constant value gas thermometer is chosen as a standard thermometer to calibrate other thermoscopes. This is a constant value gas, this is a constant value. The gas inside, okay? This is label 0, so the gas is always constant. The constant value gas thermometer is chosen as standard thermometer to calibrate other thermoscope. Okay, we look at this. This is constant value. This is the temperature you want to measure. Okay, this is called mercury reservoir. It can move up and down, up and down. Okay, this is a gas-fed bulb. This is the one. Okay, made of glass, quartz, or platinum. Depends on the temperature range over which the thermometer is to be used. Okay, yeah. Now connect to a tube to a mercury manometer. Okay, by raising and lowering reservoir R, the mercury level on the left can always be brought to the zero of the manometer scale. So in this case, the volume is constant. Ensure the volume of the confined gas remains constant. We see this is the volume is constant, okay? And on the constant volume, the temperature is proportional to the pressure, okay? This is measured in Kelvin. This is constant. Okay. If we measure the triple point of water, okay? This is the P, the pressure of the gas, constant volume gas. The P plus rho GH equal to this one. This is the P0. P0 is atmosphere, okay? Then when do the triple point of water temperature, P3 equal to C, I can get the P3. This constant is equal to this constant. So we put this one inside, we get T equal to Cp. This is C equal to T3 over P3P. And T3, we know that one is 2 point, that a triple point of water. This is 273.16 Kelvin. So this is a P over P3. Now, when we do the measurement, we find if we use different mass, the gases are a little bit different. Okay, if we use a different kind of gases, the measurement are different. So we have a little bit of trouble. And then we find out if we take the mass of gas is as less as possible. That means this is under condition limited m approach to 0. Whatever gas we use, we get the same answer. So this should be the gas is as less as possible. Okay? If temperature is to be a truly fundamental physics quantity, it is absolutely necessary that its definition be independent of the properties of the specific material. Okay? We choose the gas thermometer as our standard instrument precisely because no such specific properties of materials are involved in this operation, as we mentioned before. Use any gas, you will always get the same result. The condition is the mass is approached to 0. Okay? And we found when you measure the boiling water with the nitrogen, helium, hydrogen, they get the same answer, as long as the mass is approached to 0.
The electrical resistance of most materials increases when they are heated. Here is a device known as a thermistor that shows the opposite effect. At room temperature, the thermistor has a resistance of about 12,000 ohms, as shown on this ohm meter. When the thermistor is heated by squeezing it between two fingers, its resistance decreases dramatically. Dipping the thermistor in ice water to cool it increases its resistance.
This is some corresponding temperature. Boiling point of water, 100 degrees Celsius. This is 212 degrees of Fahrenheit. Okay, the freezing point of water is 0. Okay, and is at 32 degrees of Fahrenheit, and so on. Thermal expansion, linear expansion. If the temperature of a metal rod of length L is raised by an amount delta T, its length is found to increase by that amount delta L equal to L alpha delta T. It's proportional to its length and proportional to the temperature difference and a constant, where alpha equal to delta L over delta T. This alpha we call it constant called coefficient of linear expansion. The coefficient alpha has the unit, this don't have a unit. Delta L of L is percentage. So this is a degree. So alpha called per degree or per Kelvin. Different material has different alpha. We can check from the book.
We'll use this long iron wire to show how materials expand when they're heated. A weight is hung on the wire, and an electrical current is run through the wire to heat it. As the wire heats up, it expands and begins to sag. Increasing the temperature increases the amount of expansion. When the current is turned off and the wire cools, it contracts to its original length.
Delta L equals L alpha delta T. Above equation applies to every linear dimension of the row, including its age, the thickness, diagonals, and the diameter of the circle etched on it, and the circular hole cut in it. By metal strips, this strip is composed of two different metals. Above it, the brass, lower layer is steel. When the temperature increases, the brass has a large alpha, so it expands more. It bends. Okay, we can use to control the temperature.
Brass expands when heated. This thin brass plate has a circular hole in its center. When the plate is heated, will the brass expand inward? Will the hole become bigger, become smaller, or remain the same size? To verify our result, we compare the size of the hole with the size of this ball, which will not quite fit through the hole. We now heat the plate. After the plate is heated, the ball fits through the hole, indicating that the hole expands when the plate is heated.
This strip is made of two different metals with different coefficients of thermal expansion. If we put it in a flame, the strip bends. What will happen when we put the strip in liquid nitrogen? The strip bends the other way. This animation shows an exaggerated view of the different expansion of the separate metals as they are heated. When they are bonded together, the difference in expansions makes the strip curve. If this material is bent into a helix, heating the strip makes the helix twist further, turning a pointer which can be used to indicate temperature.
This is a linear expansion coefficient. Look at this different. This is metal. This is metal. Okay. This is the smallest diffused quartz. Okay. This is alpha. Volume expansion. If all dimensions of a solid expand with temperature, the volume of that solid must also expand. Delta V is proportional to V, delta T, and a constant beta. The beta equal to delta V over V, the relative change in volume, divided by delta T. Okay. We call it coefficient of volume expansion of the solid or liquid. And this coefficient of volume expansion and the coefficient of linear expansion, alpha for solid, are related by beta equal to 3 alpha. Now, we can prove it later.
This is a model of the first crude thermometer designed by Galileo. A glass bulb at the top contains air at about atmospheric pressure. A tube runs down from the air flask into another flask filled with water, which has risen partly up the tube. If a person places their hands on the air flask, the air expands and forces the water level in the tube down. The water level thus gives a rough indication of the temperature of the air in the bulb. We'll use this flask filled with colored water and fit it with a glass tube to demonstrate how a thermometer works. When we heat the water in the flask, it expands and rises up the glass tube. The position of the water level can thus be used as an indication of the temperature of the water. Most liquids expand as their temperature increases, but there is one notable exception to the rule: water at low temperature. We'll use this flask filled with colored water and an ice bath to demonstrate how water can actually contract as it warms. After about an hour in the ice bath, the water inside the flask is nearly at 0 degrees Celsius. The flask is now removed from the ice. We'll follow the water level in this capillary tube using time-lapse photography as the water temperature increases. The water level drops at first. The water is contracting as the temperature increases. When the temperature of the water reaches 4 degrees, normal expansion begins.
We'll use the pressure generated by water as it freezes to crack this strong iron vessel. The vessel is first filled with water. A plug is then tightly sealed into the top. And the vessel is placed in a bath of liquid nitrogen. A few minutes later, the vessel explodes. The thick iron walls were no match for the tremendous pressure generated by the water as it froze. This animation shows the pressure on the inner surface of the vessel generated by the freezing water.
Almost all metals expand when they are heated. We'll demonstrate the immense force of that expansion using this iron rod and a steel pin. The rod is placed in a strong frame, and the pin is put in a hole near the end of the rod. The pin is tightened against the frame by turning this large nut. The steel pin is now pressed tight against the frame. A series of gas jets under the iron rod are lighted and begin heating the rod. After a few minutes of heating, the expansion of the rod breaks the steel pin. This type of expansion would destroy bridges and other large metal structures, so they are designed with expansion joints that allow the metal to expand and contract without stress.
Heat capacity, temperature and heat. If you take a can of cola from the refrigerator and leave it on the kitchen table, its temperature will rise rapidly at first, but then more slowly until the temperature of the cola equals that of the room. The two are then in thermal equilibrium. In the same way, the temperature of a cup of hot coffee left sitting on the table will fall until it also reached room temperature. In generalizing this situation, we describe the cola or the coffee as a system with temperature T, system S, and the relevant parts of the kitchen as the environment with temperature TE, environment of that system. Our observation is that if TS is not equal to TE, then TS will change. TE may also change some until the two temperatures are equal, and thus thermal equilibrium is reached. Such a change in temperature is due to the transfer of a form of energy between the system and its environment. This energy is thermal energy or internal energy, which is collective kinetic and potential energies associated with the random motions of atoms, molecules, and other microscopic bodies within the object. The transferred internal energy is called heat and is symbolized Q. Look at this. If the T environment is larger than T system, heat is positive when internal energy is transferred to a system from its environment. We say that the heat is absorbed. If the TE equal to TS, nothing happened. If the TE is smaller than TS, heat is negative when internal energy is transferred from the system to its environment. We say that heat is released, lost. Definition. Heat is the energy that is transferred between a system and its environment because of a temperature difference that exists between them. Recall that energy can also be transferred between a system and its environment by means of work, W, which we always associate with a force acting on a system during the displacement of the system. Heat and work, unlike temperature, pressure, and volume, are not intrinsic properties of a system. They have meaning only as they describe the transfer of energy into or out of a system. Measuring heat unit. The calorie, Ca, was defined as the amount of the heat that would raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 Celsius. In 1948, the scientific community decided that since heat, like work, is a transfer energy, so the metric system unit for the heat should be the same as that energy, namely the joule. The calorie is now defined to be 4.1860 joule exactly, with no reference to the heating of water. 1 calorie equals 4.186 joule exactly, and 1 capital K is thousands calorie. In the British system, the corresponding unit of heat was the British thermal unit, defined as the amount of heat that would raise the temperature of 1 pound of water from 63 degrees Fahrenheit to 64 degrees Fahrenheit.
We've all felt how much warmer our hands become when we rub them together rapidly. Any two objects rubbed together will generate heat. Here is one such pair of objects, a wooden board and dowel. If we rub them together this way, not much happens. Let's try a little more speed and pressure. Now we clearly see the effects of heat generated by the friction between moving objects.
We'll use this plastic tube loaded with lead shot to show how mechanical energy is transformed into thermal energy. The temperature of the lead shot is initially 21 degrees Celsius. We'll perform mechanical work on the lead shot by flipping the tube end over end. Each flip raises the shot 1 meter, then drops it back to the bottom of the tube. We will flip the tube 10 times for a total lift and fall distance of 10 meters. The lead shot is now at 21.5 degrees Celsius. The mechanical energy of lifting the shot has been transformed into thermal energy, raising the temperature of the lead shot. We'll use this cork popper to demonstrate conversion of mechanical energy to heat and then back to mechanical energy. This hollow cylinder spins between 2 wooden arms, which can be squeezed down onto the metal. A small amount of water is put inside the cylinder. Then a cork is tightly pressed into the top. The motor is switched on and the arms are squeezed down on the rotating cylinder. Friction between the cylinder and the arms heats the water and turns it into high-pressure steam. The thermal energy in the steam pops the cork into the air.
The absorption of heat by solid and liquids. Heat capacity C. The heat capacity C of an object is the proportionality constant between an amount of heat Q that the object absorbs or loses and the resulting temperature change delta T of the object. That is Q delta T proportionality. Okay, delta T is T final minus T initial.
When we put a flame to this balloon filled with air, the balloon explodes. But But an identical balloon filled with water easily withstands the flame. The high heat capacity of the water allows the balloon to absorb large amounts of heat without a large rise in temperature.
When we touch this paper cup with the flame from a torch, it quickly catches fire. When we fill an identical cup with water and bring the flame up again, the cup withstands the flame without harm. The flame can play onto the cup long enough to boil the water inside without burning up the cup.
Specific heat, C equal to capital C over M. Two objects made of the same material, say marble, will have heat capacity proportional to their masses. It is therefore convenient to define a heat capacity per unit mass, or specific heat C, that refers not only an object but to a unit mass of the material of which the object is made. Molar specific heat. In many instances, the most convenient unit for specifying the amount of a substances is the mole, where 1 mole equals 6.02 times 10 to the 23 power elementary units of any substance. Okay. When quantities are expressed in moles, the specific heat must also involve moles, rather than a mass unit. It is then called a molar specific heat. Okay. The following table shows the values for some elementary solids. Each consists of a single element at room temperature. Okay, look at this one. This is specific heat. This is molar specific heat. We see all these lead, tungsten, silver, copper, aluminum. They have quite different number of the specific heat, but their molar specific almost the same, around 25. We will explain it later.
Different metals have different specific heats. We'll demonstrate that using equal masses of lead, aluminum, and steel shot. 75 grams of each metal are placed inside soda cans that are sealed and put into boiling water. When the metal samples reach 100 degrees Celsius, we'll pour each of them into 50 grams of water and measure the increase in temperature of the water. The lead sample increases the water temperature 4 degrees Celsius. The aluminum sample increases the water temperature 14 degrees Celsius. The steel sample increases the water temperature 8 degrees Celsius. Aluminum has the highest heat capacity of the three metals and lead the lowest.
We'll use these three metal cylinders to demonstrate how heat capacity varies for different materials. The cylinders, made of aluminum, steel, and lead, have equal mass. They are slotted to slide on small rails in this frame, which is covered with a thin sheet of beeswax. The rods are heated in boiling water to 100 degrees Celsius. When placed on the rails above the wax, they begin to melt their way down through the sheet. Aluminum, with the highest heat capacity of the three, travels farthest, followed by steel, then lead.
An important point. In determining and then using the specific heat of any substance, we need to know the condition under which heat transfer occurs. For solid and liquid, it turns out that specific heat under constant pressure and constant volume for any solid or liquid differ usually by no more than a few percent. Gases, as you will see, have quite different values for their specific heat under constant pressure condition and under constant volume condition. Heats of transformation. Matter can exist in three common states. In the solid state, the molecules of the sample are locked into a fairly rigid structure by their mutual attraction. In the liquid state, the molecules have more energy and move about more. They may form brief clusters, but the sample does not have a rigid structure and can flow or settle into a container. In the gas or vacuum state, the molecules have even more energy and free of one another and can fill up the full volume of a container. When energy is absorbed by a solid or liquid, the temperature of the sample does not necessarily rise. Instead, the sample may change from one phase of state, that is solid, liquid, gas, to another phase or state. To melt a solid means to change it from the solid state to the liquid state. The process requires energy because the molecule of the solid must be free from their rigid structure. To freeze a liquid to form a solid is a reverse of melting and requires an energy be removed from the liquid so that the molecules can settle into a rigid structure. To vaporize a liquid means to change it from the liquid state to the vacuum or gas state. This process, like melting, required energy because the molecules must be free from their clusters. Condensing a gas to form a liquid is the reverse of vaporizing. It requires that energy be removed from the gas so that molecules can cluster it instead of flying away from one another. Heat of transformation. The amount of energy per unit mass that must be transferred when a sample completely undergoes a phase change is called the heat of transformation, L. So when a sample of mass M completely undergoes a phase change, the total energy transfer is Q equal to Lm. L is the heat of transformation. Mass is the mass. In this case, process T is constant, does not change. look at that. This melting point, this boiling point, this hydrogen, this water, and so on. So water has pretty sample. Question A. How much heat must be absorbed by ice of mass M 720 gram at minus 10 degrees of Celsius to take it to liquid state at 14 degrees of Celsius? From minus 10 degrees to 15 degrees, the water undergoes three processes. First, from minus 10 to 0, that's the heating, okay? And at 0 degrees Celsius, phase change from solid ice to a liquid state. And then from 0 to 15, the liquid increase the temperature. So let's see that. Q1 is ice from what? From minus 10 to 0, okay? Now we put number inside. Okay. The mass is 0.72 kilogram. This is to 0, minus 10, we get number. And the second is the phase energy, air M. We can check the number. Air phase change from liquid solid to liquid is 333 multiply. And the last is from 0 to 15 degrees Celsius, a liquid. So this you have your water, a liquid. This is ice. They're different. Okay. The final is 15. This is 0. Okay. So we get 3. So altogether we need 3. Put them together. Okay. About 300 kilojoule. Question B. If we supply the ice with a total energy of only 210 kilojoule as heat, what then are the final state and the temperature of the water? So look at these three processes. We have three questions: whether they can reach the 0, in that case the over ice, or whether they can have a phase change completely become a liquid, or just part phase change, part cannot. Or last, they can have a phase change, but the temperature are not enough to 15 or something like that. So we check, okay. First we see from minus 10 to 0, we need 15.6 K. We have as calculated. Phase change is this one. So we see this one, we can finish this one, but not this one. That means only part of ice become the liquid, and part of ice stay as ice. So let's see, 210 minus 15 you have 164 kilo. And total phase change, we need 239.8. So our energy is not enough. Only we have a part. We divide it by the air, we get about 0.56 kilo can become water. Okay, and other is left as ice, a degree of 0 degree of Celsius. So 580 degree become the water, 140 degree ice, all at the temperatures 0 of Celsius. Sample: a copper slab whose mass MC is 75 grams is heated in a laboratory oven to a temperature T 312 degrees of Celsius. The slug is then dropped into a glass beaker containing a mass M water, 220 grams of water. The heat capacity Cp of the beaker is 45 calories per Kelvin. The initial temperature Ti of the water and the beaker is 12 degrees of Celsius. Assuming that the slug, the copper, the beaker, and the water are an isolated system, and the water does not evaporate, find the final temperature T final of the system at thermal equilibrium. We see that both the water, beaker, and the slug, the copper, they have energy, put together is constant before. And during the heating, okay, they have a change, okay? But every change, this change, zero, okay? What it means, we do this data on both sides. This is change. This is change constant, zero. What is this change? This is the heat. We have only heat involved, no work involved. So this is water, he absorbed heat, okay? This is the fever, he absorbed heat. This is a copper, they released heat. So anyway, this put together is zero. And that's what is QW? QW equal to C water, M water, T final of the Ti. What is B phase is C given T final of the T initial. They're the same. And finally, the copper. The copper is C copper, M copper, T Fi. T is larger than this one. So this negative number, it released the heat. They, water and the big, absorb the heat. So we put these three in this equation. We can find TF. Once we find that TF, we put it aside, we get a sweet number. CC, 0.6C. MC is 75. We just so about 20 degrees Celsius. And we put the TF inside where the QW equal to this. QB, absorbed. And the QC is negative number. Okay. The first law of thermodynamics. A closer look at heat and work. We put gas in a container so it can exchange heat with a thermal reservoir. Also, with the lead shot put in more or takes more, you can change the pressure of this gas. Now, we do from Pi, Vi, Ti, change, become final, P final, V final, T now. The procedure by which you change the system from its initial state to its final state is called a thermodynamic process. During such process, heat may be transferred into the system from the thermal reservoir, positive heat, or vice versa, negative heat. And the work is done by the system to raise the loaded piston. Okay, this is positive work. Or lower it, the negative work. We assume that all such changes occur slowly, with the result that the system is always in approximate the thermal equilibrium. That is, every part of the system is always in thermal equilibrium with every other part. We know the work done by the gases dW equal to F dot ds. In our case, F is parallel to ds. So F dot ds equal to FDS. And F equal to PA, pressure at amplifier. We combine A with ds, we call it the PdV, ADS. This is dV, the volume change, okay? This is the typical. dW equal to PdV, the work done by the gas. This is a differential work. And the total work, the sigma dW, or the integration of dW, equal to integration PdV, from initial state to the final state, from VI to the V final. Okay. If this work larger than zero, that means the work done by the system. If W is smaller than zero, which means the work done on the system. Work done is path dependent, depends on which way you go. Now look at this, okay? From mathematics we know this is the P versus V. And so the P dV integration actually mathematically is the the area of this below the curve, above the x-axis, between these two lines. Okay? Yeah. Now, this is the way we go I from this term. Now, if we from same I to same f, we go this way. Especially, we do the integration, this interior work much larger than this one. Right? Furthermore, when we go this way, and this one is much smaller than this one. So we know different, the path, we have different result. Okay. Now we can go this, make it as less as possible. And we go this way, we can make it as large as possible. Okay. If we go the opposite direction, okay, we know from mathematics, this is negative area space, a negative number. Okay. If you go around, okay, this is larger than rho, this is a loop. Okay. Heat Q and work W are path-dependent quantities. It depends on the path. Okay. But Q minus W is the same for all processes between two fixed points. So that gives us a lot of thinking. Okay.
This glass flask with two side arms spins freely in its support. A small amount of water in the bottom of the flask is heated to boiling by a flame. When the water boils, the steam jetting out of the arms spins the flask.
The first law of thermodynamics. When a system changes from a given initial state to a given final state, both the work W done and the heat Q exchanged depends on the nature of the process. Experimentally, however, we found a surprising thing. The quantity Q minus W is the same for all processes. It depends only on the initial and the final state, and does not depend at all on how the system gets from one to the other. The quantity Q minus W must represent a change in some intrinsic property of the system. We call this property the internal energy E internal, and we write delta E internal equal to E internal final minus E internal initial equal to Q minus W. Delta E internal equal to Q minus W. The first law of thermodynamics. The internal energy E internal of a system tends to increase if energy is added via heat Q, and it tends to decrease if energy is lost via work W done by the system. This is the first law of thermodynamics. Delta E internal equals E internal final minus E internal initial equals Q minus W. If the thermodynamic system undergoes only a differential change, we can write the first law as dE internal equal dQ minus dW. Okay. Here, dQ and dW, unlike dE internal, are not true differentials. That is, there are no such function as QPV and WPV that depends only on the state of the system. The quantities dQ and dW are called inexactly differentials, inexact. For our purpose, we can treat them simply as infinitesimally small energy transfers. Some special cases of the first law of thermodynamics. Delta E internal equal to Q minus W. 1. Adiabatic processes. An adiabatic process is one that occurs so rapidly or occurs in a system that is so well insulated that no transfer of heat occurs between the system and its environment. Putting Q equal to 0 in the first law, then let's to delta E internal equal to minus W. We can see that if the system do work is positive, its internal energy decrease. Okay. Adiabatic processes, Q equal to 0. So delta E internal equal to Q minus W equal to minus W. This tells us that if work is done by the system, that is, if W is positive, the internal energy of the system decreases by the amount of the work. Conversely, if the work is done on the system, that is, if W is negative, positive, internal energy of the system increase by that amount. Let's see adiabatic process. This container all are insulated, so no heat exchange be possible. So only it can change the works. Okay, so this less shock to the system. Okay, Q equal to 0. Now with the delta E internal equal to minus W. This figure shows an idealized adiabatic process. Heat cannot enter or leave the system because of the insulation. Thus, the only way energy can be transferred between the system and its environment is by work. If we remove shock from the piston and allow the gas to expand, the work done by the system, the gas, is positive, and the internal energy of the gas decreases. If instead we add some shock, and compress the gas, the work done by the system is negative than positive, and the initial energy of this gas increases.
Did you ever wonder why a small fog appears at the top of a bottle of soda when it's opened? Here is another demonstration of this effect. A sealed bottle contains air with a small amount of water on the bottom. If air is now pumped into the bottle, the pressure will increase until it blows the stopper off the bottle. This sudden expansion of the air, known as adiabatic expansion, expends energy too rapidly for thermal energy to be brought in from outside the container. The air therefore uses its own thermal energy for the expansion and cools as a result. A thermistor has been mounted inside the bottle to measure the temperature of the air. As the pressure increases, the temperature of the air inside the bottle increases. When the stopper blows, the air in the bottle expands, causing the temperature inside the bottle to decrease rapidly. When the temperature decreases below the dew point, fog is formed.
Have you ever noticed that a bicycle pump gets warm as it is pumped? When a gas such as the air in the pump is rapidly compressed, it heats up. We'll use this fire syringe to demonstrate the heating due to compression. A small wad of cotton wool is placed at the bottom of this thick glass cylinder, and a tightly fitting piston placed inside. When the gas is compressed by rapidly pushing down on the piston, the cotton bursts into flame. Here's the action repeated in slow motion.
Two, constant volume processes. If the volume of a system, such as a gas, is held constant, that system can do no work. Putting W equal to 0 in the first law yields W equal to dW integration equal to PdV equal to 0. Then, why? Because constant volume, the volume does not change. It's 0. Okay, always 0. Yeah. And then delta E equal to Q minus W equal to Q. Thus, if heat is added to a system, that is, if Q is positive, the internal energy of the system increases. Okay. Conversely, if heat is removed during the process, that is, if Q is negative, the internal energy of the system must decrease. 3. Cyclical processes. They are processes in which, after certain interchange of heat and work, the system is restored to its initial state. In that case, no intrinsic property of the system, including its internal energy, can possibly change. They're putting delta E equal to 0 in the first law, yields Q equal to W. Thus, the net work done during the process must exactly equal to the net amount of the heat transferred. The store of the internal energy of the system remains unchanged. Cyclic process form a closed loop on the pressure volume plot. We shall discuss such processes in some detail later. Free expansion. This shows how such an expansion can be carried out. A gas, which is in thermal equilibrium within itself, is initially confined by a closed stopcock to one half of an insulated double chamber. You have double chamber, it's only half. The other half is evacuated, this vacuum. The stopcock is open, and the gas expanded freely to fill both halves of the chamber. No heat is transferred to or from the gas because of the insulation. Okay. No work is done by the gas because it rushes into a vacuum. Okay. Its motion unopposed by any counteracting pressure. 4. Free expansion. These are diabatic processes in which no work is done on or by the system. Thus, Q equals W equal to 0. And then the first law requires that delta E equal to 0. A free expansion differs from all other processes we have considered because it cannot be done slowly and in a controlled way. As a result, at any given instant during the sudden expansion, the gas is not in thermal equilibrium, and its pressure is not the same everywhere. So, although we can plot the initial and the final state on a PV diagram, we cannot plot the expansion itself, only 2 points, not the process. Okay, the first law of thermodynamics, 4 special cases. The first law is delta E internal equal to Q minus Z. Process, adiabatic, Q equal to 0. So delta E equal to minus Q. Constant volume, W equal to 0. Delta E equal to minus Q. Cyclic closed. Delta E cyclic equal to 0. We go back to original. So Q equal to W. Finally, free expansion, Q, W 0, delta equal to everything is 0. We have a sign convention. W larger than 0, positive means done by the work. W smaller than 0 means done on the system. Q larger than 0 means heat added to the system. Q smaller than 0 means withdraw energy from the system. Okay. How to remember that one? We use the steam engine. Steam engine, okay, exhaust works, do works, okay, and produce heat. Sample. Let 1.00 kilogram of liquid water at 100 degrees C be converted to steam at 100 degrees C by boiling at a standard atmosphere pressure, pressure to give to you. In the arrangement of the left figure, you have heat exchange, you have the work we do. Okay. The volume of the water changes from an initial value 1.00 times 10 to the minus 3 cubic meter as a liquid to 1.671 cubic meter as steam. Wow, huge expansion. Okay? Question A. How much work is done by the system during the process? Temperature is constant. Okay. Pressure is constant. Okay, in this case. So the work done equal to P dV. The pressure is constant. Okay, it never changes one. So take P out, become P delta V. Okay, delta V. V final and initial. Right? Yeah. So we put number inside. This is a Pascal. This is the volume change. Huge change. So the work is very big. Okay, about 169 kilojoule. Question B. How much energy is transferred as heat during the process? Find the Q. Okay. Now, Q, this is just 100 water to 100 gas equal to air M. This is we can check from the table. Okay. The mass is 1.00 kilogram. So get out Q. Question C. What is the change in the system's internal energy during the process? By formula, delta E equal to Q minus W. Okay, W. And we know Q squared. We know W, 6M, polystyrene. You get change, increase. Heat transfer mechanisms. First, conduction, which is a two reservoir, hot reservoir at temperature TH, cold reservoir at temperature TC. Between them, we have a slab of a material. There's this K depends on material. The thickness air, the cross area is A. The TH is larger than TC. We see the heat transmit from this side to this side, pass through the slate at unit time is P conductor, is Q over T. It is depends on the material, K, and the cross area, A. Definitely, the larger A, the larger Q, right? Also, it depends proportional to temperature difference, HT, TH minus TC, and inversely proportional to its thickness L. We move K to down. You can rewrite it as ATH minus T hot R, where R equal to air over, we get a called the thermal resistance. Okay, here, K is the thermal conductivity of the material. Okay, A is the cross-section area. Okay, L is the thickness of the sample slab. TH is the temperature of the hot reservoir. TC is the temperature of the cold reservoir. And R we call thermal resistance. The higher the R, the lower the K. There's poor conductivity and a good thermal isolator. These are some thermal conductivity. We will see water, glass is about 0.1, and the silver is very, very good conductivity, heat conductivity. Okay. Conduction through a composite slab. Here we have two slabs instead of one. This is K1, K2, L1, L2, the same cross area A, and the temperature between the contacts is Tx. We don't know. Okay, this is a hot reservoir at Th. This is a cold reservoir at Tc. When this is a standing state process, very standing, then we know that the heat passed through this slab 1 equal to the heat past slab 2 because they are standing. Okay, so in this case we see that we write it. The P, the heat conductor passes through 2. It can write K2A Tx Th minus Tx over L2 equal to K1A, okay, this is just Tx minus Tc over L1. This is physics. When in a state process, the heat passing through 2 is equal to heat passing through 1. From this equation, I can find Tx, the temperature on the between them. Okay. Once we find the Tx, we put it back, we can find the P. These are junior high school mathematics, so I'm not going to do it. We just get the answer. Look at this answer. We know L over K, we call it R. This is R1, this is R2. So this one, that heat conducted through this slab is A Th by Tc sigma R. Instead of R, we have a sigma R. So that's very interesting. If you have 3, we get a 3. R1, R2, R3. We have 1, we get R1. This formula is exactly the same as the previous one. This R called is a property attributed to a slab of a special thickness, not a material, because same material, different thickness, K will be different. Okay. The second way is convention. Okay. When you look at the flame of a candle or a match, you are watching thermal energy being transferred upward by convention. Such heat transfer occurs when flow, such as air or water, is in contact with an object whose temperature is higher than that of the fluid. Convection is a part of many natural processes. Atmospheric convection plays a fundamental role in determining global climate patterns and daily weather variations. Glider pilots and birds alike seek rising thermals, the current of warm air, that keeps them aloft. Huge energy transfers take place within the oceans by the same process. The third way is the radiation. The third method of heat transfer between an object and its environment is by electromagnetic waves. Visible light is one kind of an electromagnetic wave. Heat transfer in this way is often called thermal radiation, the heat. The rate P radiation at which an object emits energy via electromagnetic radiation depends on the object's surface area A and the temperature T of that area in Kelvin, and is given by P radiation of the object is sigma epsilon A T to the fourth, where sigma is a constant, we call Boltzmann constant, and epsilon we call E, we call it represent the emissivity of the object's surface between 0 and 1. 1 in the maximum, the black color. The rate P absorbed at which an object absorbs energy via thermal radiation from its environment, which we take be a uniform temperature T environment, is P absorbed equal to similar sigma E A T to the 4. Instead, the T of the body, we can T environment. So, and an idealized black body radiator with epsilon equal to 1 will absorb all the radiated energy it intercepts. This is the one. So heat color blocks will absorb heat strongly, okay, and emit heat strongly too. Okay. Then the net rate P net of energy exchange due to the thermal radiation is P net equal to P absorbed minus P radiated. So it's sigma epsilon A T environment force minus T to the fourth. Sample. The figure shows a cross-section of a wall made of white pie of thickness LA. This is one. white pipe, thickness La. And the bricks of thickness LD. LD is equal to 2 La. This is double this La. Sandwich two layers of unknown material with identical thickness and thermal conductivity. You have two same thickness. I don't know what material, okay? But their conductivity is the same, thickness is the same. The thermal conductivity of the pipe is Ka, and that of the block is Kd. Kd equal to 5.0 Ka. So much easier to transfer heat. The face area A of the wall is unknown, but they are the same. Thermal conductivity through the wall has reached steady state. So this is steady state. The heat passes through this, passes through this, passes through this, passes through this. At the same time, it's the same. Okay, steady state. They only know interface temperature as T1 we know, 25 degree. T2, 20 degree. Okay, T2, 20 degree. T5, minus 10 degree. What do I want to find? What is the temperature T4? And we look this one, we know T1, T2. Okay, so the pass A, the energy pass A is Ka, area A, T2 minus T1, T1 minus T2 with area A. Okay, and PD is Kd, same A, T4 minus T5 over the D. In a state of a stating way, they are the same. Okay, we know there's T1, T2, we know LA, we know LD, we know KD, KC, T4. So we can find these three equations, we can find the T4. T4 equal to Ka, LD, T1 minus T2 over KD, LA plus T5. And then we know that LD is 2LA and KD is 5LA. So we put this number inside, okay, we get the T4 equal to minus 8.0 degree of Celsius. These are junior high school maths, so I'm not getting into the detail. It's very easy, okay. The key point is this point. This is a physics part. Next chapter, chapter 18, the kinetic theory of gases. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college of physics during 1990 to 2021, based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.